Hello again. In this video, we're going to look at the determinants as area or volume. This is the last video on determinants. Let's start by looking at the following theorem. If A is a 2 by 2 matrix, then the area of the parallelogram determined by the columns of A is just the absolute value of the determinant of A. We'll stop right there for now. But we'll see in a little bit that with the 3 by 3, it's going to end up being the absolute value of the determinant. It's going to end up being a volume of a parallelogram in 3D, which is called a parallelepiped. I'm going to start with the most simplest case, a rectangle, because we know the area of this is this length times width, which is A times D. So let's let this be U and this be D. So let's let A be the matrix UV, which would be A0, 0D. And you can see that the determinant of A is just AD. Now, they do put absolute values here because we could have switched those around and you would end up with a negative. But in this case, it is going to be AD, which is the area of that rectangle, where U was that vector and V was that vector. So let's look at case 2. Let's find the area of this parallelogram, which, by the way, we still know is A times D. The area of a parallelogram is still the length times the width, or the base times the height. And let's see if the determinant still works there. And by the way, this is a horizontal shear transformation. You could do it that way too. We will in general in a minute. But let's just look at this simple. Let's call this U, and then that would be this vector. Let's do it in a different color. And let's call V this vector. So this vector would still be D on the Y, right? But let's just label it C, since I don't know what that is. So that would be V. So A, let's let A be our new UV, which is still A0, but now it's CD, and you can still see that the determinant of A, the absolute value, is still AD. Which we know is an area of a parallelogram. So let's do the general case. What if your U is not on the x1 or the x-axis? Say this is our U and this is our V. So let's just in general let U be AB and let V be CD. So A, which is UV, is equal to our general little formula, and the determinant of A is equal to AD minus BC. So we want to show that the area of this parallelogram is AD minus BC. So this is another transformation. So actually this was up here was a shear transformation. This one is going to be a rotation transformation. So that's what I'm going to do. I'm going to let T go from R2 cross R2 to R cross R2, where T of X equals our standard matrix transformation, where A is now going to be a rotation. This is actually a clockwise rotation. It says here T is the transformation that rotates each point in R2 about the origin through theta with a clockwise rotation. We in the past did a counterclockwise, but I want this one to be clockwise because what I'm going to do is I want this to go down to the x1 axis. So then I just end up with case 2. By the way, I should have added, we want to show. So that way we can show that the determinant of A is actually AD minus BC. By the way, if you let theta be a negative phi, you would end up with the formula that we had in the book for the counterclockwise. Okay, so let's go ahead and do that. So let's look at T of U, which we know is AU, which, by the way, A is this, and U was AB. And if you multiply that out, that would be equal. And let's call this U sub T, where U sub T is, what we did is we rotated this by an angle of theta. I'll call that little angle in there theta, where you have UT sitting right at that x-axis. Now let's do the same thing for T sub V. T sub V is going to be the same thing, but with CD. And we'll call that V sub T. And again, maybe we should make this a little smaller. V sub T is going to be somewhere. Well, it's not proportionally right, but that's going to be the angle there. So you can see it's going to be the same area, isn't it? Oops, went a little too far. Okay, so now what? Since it's the same area, we should be able to take that matrix, U sub T and V sub T, and find the determinant, the absolute value, and we should be able to get that answer. And furthermore, we saw that in case 2, that the determinant of UV, U sub T, right, U sub T and V sub T, is the area of that parallelogram. So let's see if this becomes out to be AD minus BC. But before we do that, we need to look at what is UTVT, because if you remember, I almost forgot, in our original transformation, it's R2 cross R2, and I just did R2 here. So we need to really look at R2 cross R2, because this is equal to T of U and T of V, which is AU plus AV, which we know is AUV, and A is our rotation matrix, and U is AB, and V is CD. That's the determinant I want to use here. So we're going to say this is equal to the determinant of these two things. And what is that equal to? Oops, I put my absolute value in the wrong spot there. So that is equal to the determinant of A times the determinant of B, since this is a product of two things. We're almost done. I need more room. And here it is. Let's find the determinant. This 2 by 2, that's cosine squared theta minus a negative sine squared theta. And this is AD minus BC. We got it, because cosine squared plus sine squared is 1. So what does this mean? Let's make this a little smaller so we can see the whole thing. We wanted to show that the determinant A is the area of this triangle. We figured, and we know the area of this is the same as the area of our original, so therefore the area of our original is AD minus BC. Pretty interesting. Oh, and by the way, we know that because of case 2. Right? We proved that the area of a parallelogram when it goes through the x-axis is the determinant. So we have it. So let's look at example 4 in the book. It says calculate the area of a parallelogram determined by the points -2, -2, 0, 3. So here's -2, -2, 0, 3, 4, -1, and 6, 4. And notice how it doesn't go through 0, 0. So we're just going to translate it up. I'm going to look for this vector and this vector. So again, this is the point -2, -2, and this is the point 0, 3, and 4, -1. Those are the 3 points that I need. So I'm going to call U my vector. And what that's going to be is going to be this distance here, -1 minus a -2. And the y, that's the y coordinate. The x coordinate is going to be 4 minus a -2. And the y coordinate will be -1 minus a -2. Or the x1 versus x2 coordinate. So we have 6 and 1. And you can see here that if you use this vector, that will be like taking the vector 6, 1, which is right here. This vector right here. And similarly with B, we're going to use these 2 points. So the x-coordinate would be 0 minus a -2 and a 3. So new minus the old. So that would be the point 2, 5. 2, 5 is right here. So that would be the V, and this is the U. So all I got to do is find the determinant of U, V. And I'm going to take the absolute value just in case. And that's the determinant of the U, which is 6, 1, and the V, 2, 5. So that would be 30 minus 2, which is 28. And just in case you did V cross U and it became negative, you can put the absolute values there. So that would be the answer for the area for example 4. So now let's look at the volume. So it says here, if A is a 3 by 3 matrix, the volume of a parallelepiped is determined by the columns of A, right? So the 3D parallelogram determined by the columns of A is the absolute value of the determinant of A. The proof for this, or to show this, is very similar to a 2 by 2, so I won't be doing it. The book, by the way, does have another way even to prove the 2 by 2. I didn't mention that before. Than I did. So you can look at that as well. But you can also check out, there is an explanation of why it works and the pictures of what it looks like for a 3 by 3. Here's a picture. So they do something very similar. They start with a rectangle, and using that rectangle, they stretch it. And there is that parallelepiped. So here we're going to have it says find the volume with one vertex at the origin and vertices adjacent at these 3 points. So go ahead and pause this, see if you can do it, and then come back for the solution. Here's the solution. The volume is just determined by the 3 columns. Since one of the vertices is at the origin, and we subtract those, this will be the first vector, the second vector, and the third vector. So we just take the determinant, which is 18.